A quantum computer is impressive. It processes information according to the laws of quantum mechanics. Quantum computers use superposition, entanglement, and interference. They require extremely precise control and extremely low temperatures. A quantum computer is not simply a classical computer that runs faster. It processes information according to fundamentally different physical rules. A classical computer uses bits. A bit represents either a 0 or a 1. A quantum computer uses a bit's quantum mechanical analogon, a quantum bit or a qubit. There has been a whole video on qubits already, so make sure to check it out in case you haven't seen it yet. A qubit can be prepared in a superposition of 0 and 1. That does not mean that it is simply 0 and 1 in the everyday sense, but it means that the quantum state contains amplitudes associated with both possibilities. When we measure the qubit, we still obtain an ordinary result, 0 or 1, but before the measurement, the quantum state can evolve in a way that has no direct classical equivalent. Several qubits can also become entangled. When qubits are entangled, the information is not stored only in the individual qubits, but also in correlations across the entire system. Finally, quantum gates can manipulate these superpositions and correlations. During a running quantum algorithm, many possible computational paths can contribute to the final result. Through quantum interference, paths leading towards useful outcomes can reinforce one another, while other paths can cancel out. The final measurement produces classical information, but the calculation that produced that result followed quantum rules. Now, this does not make a quantum computer better at every task, but for carefully selected problems, quantum computation may offer a major advantage. However, there is one problem. Most quantum computers are currently quite lonely. They are isolated and not connected to a network. Now, if you think of your classical computer, just as the one you're watching this video on right now, you would surely agree with me that having a computer is great, but this computer being connected to the internet is when things get really powerful. So perhaps the future of quantum computing is not simply a bigger quantum computer, perhaps it's a quantum computer with friends. Quantum computing began with a slightly rebellious thought. If nature follows quantum mechanics, perhaps our computers should stop pretending that it doesn't. There were several researchers that helped transform this idea into a scientific field. Paul Benioff, for example, showed that computation itself could be described quantum mechanically. Richard Feynman then gave this idea a clear purpose. Simulating a quantum system on a classical computer can require enormous computational resources, so Feynman simply asked, well, instead of forcing a classical system to imitate quantum physics, why not use a controlled quantum system to simulate another? David Deutsch then developed the concept of a universal quantum computer, a machine that could, in principle, perform any physically allowed computation. And finally, Peter Shor showed why building one might actually be worth the trouble. He developed a quantum algorithm that could factor large numbers fundamentally faster than the best-known classical algorithms. And that was how quantum computing went from an interesting theoretical idea to something with potentially enormous practical consequences. What began as a thought experiment became an engineering challenge. Build a quantum system, control it precisely, perform useful calculations with it, and somehow convince the rest of the universe not to interfere, which unfortunately is not something the universe is particularly good at. The word qubit describes the fundamental basic unit of quantum information. It does not describe one specific physical object. Therefore, a qubit can be realized using many different platforms. In fact, there is a big zoo of platforms and they deserve a very own video. Just keep in mind that there are several of them and that each platform has its own strengths. Some preserve quantum states for a long time, some allow very precise operations, some are easier to connect to light, some are easier to fabricate on a chip, etc., etc. Now imagine that we eventually build useful quantum processors. Again, if we have a look at our classical computing world, connecting classical computers made it possible to share information, access remote resources, and combine specialized machines. The internet did not simply make each individual computer faster, but in fact it created capabilities that no individual computer could provide alone. It could be the same in a quantum world. A quantum network could connect processors, quantum memory, sensors, and communication devices. Small quantum processors could work together on larger calculations. A user could remotely access specialized quantum hardware. Quantum sensors could share entanglement to improve measurements, etc., etc. The long-term vision is often called the quantum internet. A quantum internet would not simply be today's internet and fancy and with a few more lasers attached, because quantum information behaves very differently from classical information, and unfortunately, it is a rather demanding network guest. Issue number 1. Classical information can usually be copied. If a signal becomes too weak, we can measure it, regenerate it, and send a fresh copy onward. That is essentially what classical amplifiers and repeaters do. Quantum information does not allow us to proceed so casually. An unknown quantum state cannot be copied perfectly. That is the no-cloning principle. We can also not simply measure the state, write down the result and reconstruct it later, because a measurement generally changes the quantum state and destroys the superposition or entanglement that we really want to preserve. A quantum network therefore needs interfaces that transfer quantum information without first reading it. It needs quantum memories that preserve states while connections are established, and over long distances, it will need quantum repeaters. As said, in a classical network, a repeater can receive, amplify, and retransmit a signal. A quantum repeater cannot simply copy an incoming qubit. Instead, quantum repeater protocols aim to distribute entanglement across shorter segments and then connect those segments using operations such as entanglement swapping. That is already technically difficult, but there is another fundamental complication, issue number 2. The physical systems that are best for processing quantum information are not necessarily the systems that are best for transporting it. The quantum processor and the quantum network may speak completely different physical languages. At least as of 2026, superconducting qubits are among the most developed platforms for gate-based quantum computing. Those are circuits that are fabricated on chips and cooled to temperatures of only a few tenths of millikelvin above absolute zero. Now, superconducting quantum processors are usually controlled and read out using electromagnetic signals at frequencies of a few gigahertz. Microwave signals. So these processors speak microwave. Inside a dilution refrigerator, this works very well. The processor is cooled, the microwave environment is carefully controlled, and thermal noise is strongly suppressed. However, outside the refrigerator, at room temperature, the situation changes fundamentally. Just as a background information, the energy of a single photon is proportional to its frequency. And because microwave photons have relatively low frequencies, each microwave photon carries relatively little energy. Now at room temperature, thermal radiation can therefore produce many unwanted microwave photons, and this delicate quantum microwave signal can quickly become buried beneath thermal noise. Now, for short distances, it is possible to connect superconducting systems using cryogenic microwave links, basically combining 2 fridges with a third one. That is useful inside a lab or maybe a future quantum data center. But for communication between cities, we would definitely need something else. Just imagine cooling an entire cable between 2 distant cities to almost absolute zero while maintaining high vacuum. Yeah, scientifically interesting, but perhaps not the most economical infrastructure plan. For long-distance communication, optical photons are actually much more convenient. Photons at telecom wavelengths can travel through optical fibers at room temperature. They can cover long distances with relatively low loss. And conveniently, a global optical fiber infrastructure already exists. This creates a natural division of labor. Superconducting processors can perform local quantum operations using microwave signals, and then optical photons can carry quantum information through long-distance networks. The problem is that microwave and optical frequencies are separated by almost 5 orders of magnitude. So the processor speaks microwave, the network speaks light, and we definitely need a device that connects these two regimes, basically a quantum translator. Future quantum networks will probably be hybrid. They may combine superconducting processors, atomic memories, photonic communication channels, and many other systems. Each component can be chosen for the task it performs best. But these components must still exchange quantum information. And if we just have a look at those superconducting processors, one important challenge is converting a microwave photon into an optical photon. This is called microwave-to-optical transduction. The idea sounds simple. A microwave photon enters the device and an optical photon leaves. Unfortunately, there is a lot more than just the energy that we have to consider. This photon also carries a superposition, a phase relation, or entanglement with another quantum system. And the transducer must preserve all of this information during the conversion. A useful quantum transducer therefore needs several properties. It should convert photons with high efficiency. It should introduce very little noise. It should preserve the quantum coherence and, ideally, it should operate reliably, and it should not heat the millikelvin environment of our superconducting processor. Naturally, while the idea is pretty simple, satisfying all of these conditions simultaneously is the difficult part. The transducer really acts somewhat like an interpreter, so it listens to the microwave photon on the one side, it communicates with the optical photons on the other side, but it must translate without learning the message, copying the message, or adding some own creative interpretation. Let's zoom out a bit. A global quantum internet will require better memories, lower losses, more efficient interfaces, robust quantum repeaters, and reliable control systems. The basic idea is becoming increasingly concrete. The quantum computer of the future may not be one enormous machine containing every possible component, but instead it may be a network of specialized systems. One system performs calculations, another stores quantum information, another generates optical photons, another converts between microwaves and light, and the network allows them to function as one large quantum machine. Because even in the quantum world, interesting things can happen alone, but the really exciting things happen when you're connected. What should we remember? Quantum computers work fundamentally different than classical ones, but just as classical computers, they can show their full potential when they are being connected. There are two challenges. One, quantum information, just as classical one, is attenuated and lost over time. Classical information can simply be copied and reinforced, while for quantum information, we will need quantum repeaters who do not copy or interfere with the quantum state. And second, many quantum processing units and the connecting network units speak frequencies that differ by several orders of magnitudes in energy, meaning that we will need a translator to connect these two systems. This is called microwave-to-optical transduction, and there are several platforms exploring it right now. So, what do you think is the best and biggest challenge for the quantum internet? Is it quantum memories, quantum repeaters, photon loss, microwave-to-optical transduction, or is it simply getting all these extremely sensitive systems to cooperate without one of them having a quantum breakdown?